Hello, my name is Andreas Lund Rasmussen, and I have a case project about the use of acoustic emission sensors to estimate the amount of air in water. But also it can be used to try to find a flow profile and stuff like this. But these things will be investigated in a larger degree in the next semester. So what we have been choosing is some density and flow transmitters, and we will try to use this in combination with these accelerometers to try to find out and analyze this multi-phase flow. This data from the sensors are put in some CSV files, and I have made a MATLAB program that imports this data for further analysis. One thing, so as I already mentioned, next semester we will dig more into the analysis of what's happening. Now we have more focus, also focus on the sensor raw data. So you can see here there's a HMI that some teacher or student have been taking picture of. So it's more or less like a P90. And the process here is just like a simplified separation process in an oil rig, where there comes up multi-phase flow up from a production well and enters into a separator. So what's happening then is that this can be the well, and with oil, water and air coming in here. So from here you can simulate that this is a well coming into this straight pipe segment where there's a lot of measurements and the acoustic emission sensor, densitometer and stuff. And then it goes out and into a separator where we separate water and oil and gas out at the top by the use of the gravity force. And then it goes into a water tank, and then out of the water tank and pumped through the flow meter we're using, and then into the mixer again, and then just circle around. But oil will not be used in this study, just air will simulate gas and water is water. So the location of the sensors we use here, you have one flow meter here that we use for measuring the amount of water in the flow, and we have a densitometer at the end of the straight pipe segment. Right before the densitometer we have two emission sensors, and right after we have one emission sensor. So you can see a picture here that have been taken by some people working at the university or some students. So you see the flow coming in here from the left and through the densitometer, and then the outlet is on the right side. So at the right side, 0.2 meter from the outlet, you have some emission sensor that is mounted on the cross-sectional area of the pipe. And 1.5 meter from the outlet, we have two emission sensors, one smaller one at the top and one bigger at the bottom. The bigger at the bottom is the same size as emission sensor 1 at the outlet. So when we log this data, there have been done two different ways. So the emission sensors have been logged by an oscilloscope for approximately 2 seconds. And there are 16,000 samples, and that gives approximately 8 kilohertz sampling rate. And the densitometer and flow meter have been logged into MATLAB where we have around approximately 17 samples over 17 seconds. So that gives a sampling rate of 1 hertz. So ideally, the sampling time and sampling frequency should be the same for both sensors, but this is not the case. So these 2 seconds with acoustic emission sensor data should be assumed to have the same, to represent all the 17 seconds where you have the density meter and flow transmitter. But this is could be a very wrong assumption, but it would be a rough one. Some sensor data have been provided by the university, but some have not. So if you look at the tag number of this flow transmitter, it have a range from approximately 50 to 500 liters per minute, and it have a decent accuracy of 0.3% of this span of the range of the transmitter, plus minus this value. But the density meter, we don't have any data at all, so there's not much to talk about. As we talked about, there was two different sizes of these emission sensors. So you have one that is type 4332, and actually you have two of those, and those are the bigger ones. That's easy to see here because it's 30 grams, and you can see also that the other one is like 2 grams, so there's a big difference there in the relationship. And this size follows you can see that other parameters. If you see the voltage sensitivity is very low if you have a small sensor, but it's pretty high if you have a big sensor. And if you notice the location of the sensors, then you see the small one are on the top and in the middle of the pipe. So that has the smallest one are on the top of the pipe, so that have the lowest sensitivity, and we assume that if the water don't mix very well, that there is maybe a lot of air in the top of the pipe and not at the bottom. So that makes sense then that the most sensitive sensors are in the middle and at the bottom of the pipe. And you can also see that the more sensitive the sensor is, the lower frequency range it has. Okay. And here we have the data from dataset 3. On the left side you see the raw data plotted, and also the data after it have been through a moving average filter. On the right side we see the histograms that shows the distribution of the samples. On the flow transmitter and the density meter, there's only like 17 samples, so it's not easy to make a good distribution for these, as you can see on the right hand side. But if you follow the theory in this course, you can use a student t distribution for this due to this low amount of samples. If we look into the emission sensors, we have 3 emission sensors, and you can see in red you have the original signal, and the blue is the moving average value, the value after the filter. So it appears to be some noise on the signal, and if you look on the mean value, it seems to be some relationship here. The mean value seems to be changing and seems to be different from the 3 sensors. So the understanding is that this is of interest, that the mean value. And if you look at the right hand side, you see that there's a good spread of the data from plus minus 40 millivolt in the distribution here, but after the moving average it's a lower spread, so, and gives a nicer normal distribution, or closer to normal distribution. And the same goes to the other 2 sensors. It gets a little bit better after moving average filter. If we look on the next dataset number 10, we can say much of the same. And what you can say that, okay, this distribution of sensor 1 is maybe not normal distribution, but it seems to be a little bit lower spread at least. But if you look at sensor 2 and 3, it looks pretty close to normal distribution if you look at the value after the moving average filter. The last data set, you can see that there are a lot of, not a lot, but there are some spikes that go pretty high, like 500 millivolts, so on the original signal. And after the moving average filter, it's seems to be not that much. So maybe this information is of interest, but what I have assumed here is that this is noise, but using this moving average filter, maybe you remove some important data, so that is important to keep in mind. If you look at the distribution, you see that there is a pretty good spread, and after the moving average filter is pretty small. And actually, for all these three sensors, it looks to be pretty close to normal distribution. So if we then try to compare the data and try to see if there is some relationship with the mean value and how much air there is in this pipe, we can try to do a simple analysis, but one thing we could also talk about is that the flow and density measurements, we assume that there's a low uncertainty for these measurements because they are transmitters, and I assume that these are well-known instruments that have a good accuracy. And also one comment is that the airflow does not seem to influence the density of the flow, no, the density of the medium. So I had a suspicion that if you have more air, the density would drop, but if this is the case, it seems to be in a so small degree that it's actually not sure if the change is due to the accuracy of the transmitter or if it is actually the reason it's changing. So that assumption was a little bit wrong, it seems to be. Also, there have been a comment that water and air didn't mix very well, and when I read that, I would assume that most of the air would be in the top of the pipe, and as the more air you get, the lower it climbs. So and if you have enough air, it would go all the way down. And also, when we have this moving average filter on the sensor data, we need to be careful. As I already mentioned, if we have a too high value, then we don't get the sudden changes. So it doesn't see the quick changes. So that is, and also you can filter out important information. Okay, so if you look at this plot or this figure, we can see at the data set number 3, we have approximately 2 millivolt at the top, and the emission sensor 1 and 3 have more or less -7 millivolt. So then I assume there's no air here. The higher the voltage is, the more air there is the assumption. So I would assume there's a little bit air at the top here. If we move on the next data set, I would assume, since the value of emission sensor 2 is more or less the same, I would assume that there was more or less the same amount of air at the top here. But if you see at emission sensor 1, it seems to be getting a higher value here. So I assume that the air is traveling. There's a little bit more air in the system, and now it's also detected a little bit by this emission sensor 1. But it's not climbed all the way down to emission sensor 3 because it's more or less the same value. If we then look at the last dataset, number 18, I see that emission sensor 2 have a little bit lower voltage, as this is only the main values. If I didn't say that earlier. Anyway, there seems to be a little bit less air here, and for some kind of reason, there seems to be a little bit less air at emission sensor 1, 2, and there's a very low value for this emission sensor 3. So I will assume that there's a little bit air at the top and a little bit at the center, but not much, but a little bit at the top and at the middle. So the conclusion here is that there seems to be a connection between the mean emission sensor values and the airflow. Since the sensor data does not have a perfect normal distribution, this assumption would give some uncertainty when it comes to standard deviation and statistical data, because standard deviation assumes normal distribution, the way I made data in the tables. We could also use some frequency analysis and get maybe a better analysis. And when you think about the moving average filter I've used, then it could be the case that if there are some frequency components that describe much of the things we are interested in, then this could be filtered out. So maybe it would be better to do this frequency analysis, and then after doing that, think about how much you should filter out with a moving average filter. And that is all for me now. And in the next semester, I will try to do a much more thorough investigation